We're going to start 3.2 called maximum and minimum values. And some of what we're going to do in this section is going to feel a little bit like what we did in 2.8, okay? So to start with, we're going to talk about some vocabulary that you've probably heard before. Maybe not, though. The first vocabulary that we're going to look at is the word relative extrema. So relative, another word that your book or some books will sometimes use, I can't remember which one your book uses, is the word local. So sometimes you hear the word local extrema, or sometimes you hear the phrase relative extrema. So a point on an open interval on which f of c is a maximum or a minimum value is called a local or a relative extrema. Notice that the derivative at this point is either 0 or it doesn't exist. And I think a picture is in order to justify what they're describing. So if, in fact, I have a location where I have a peak or a valley, this particular point in any of these four graphs is a location where the derivative is 0, right? Horizontal tangent line. Or the derivative does not exist. And these points are called relative or local extrema. So you might be kind of thinking like, okay, what's the special word relative? So extrema means something that's an extreme value, right? It's extreme. It's the biggest. It's the smallest. Why am I using relative? Well, because the graph actually could do something like this. And these 2 points would be relatively the largest or relatively the smallest value nearby where they are. In a small closed-in sampling of whatever, it's the biggest thing there is. I always like to give an example that you guys do this all the time when you say somebody is tall or somebody is short. You're using them in comparison to something else, right? So if I tell you that my husband is tall, I think he's tall because I'm not. I'm quite short. But compared to the basketball team, he's not tall. Okay? He's 6'2". He's not short, but he's not like the tallest person ever, right? But relatively speaking, if he comes to any activity in my family, he's the tallest one there. He's a relative maximum value, his height is anyway. Likewise, if I'm with his family, I'm about the shortest person there. There's about 3 of us are about my height, all 3 ladies. But I'm relatively short in his family. Am I the shortest person ever? No. I have a sister-in-law on my side of the family who's like 5 foot. She's like right here. Okay? I'm not short compared to her, but relatively speaking, in that specific domain, right, in that area of whatever, it's the smallest or the largest value. All right. So the other thing that this kind of brings into play is the idea of something called critical numbers. Critical numbers are numbers, x values, where you actually have a place where the derivative is 0 or the derivative doesn't exist. So when you have these places where the derivative is 0, the derivative doesn't exist, they are potential places for relative extrema. It doesn't mean they have to be places where they have relative extreme values, but they're places where we might have maximum or minimum values. So you might be thinking, and this is the test question that I haven't graded, but you had this question basically on your test. It asked something kind of about this. It asked about the idea of taking a derivative, and what happens if you get a derivative as 0? Do you for sure have a maximum or minimum value? The answer is actually no, you don't. And the classic example of why is the graph like this of y equals, and I know I don't have it on an actual equation axis, a Cartesian coordinate plane, but y equals x cubed. The point there in the middle has a slope of 0. This is the visual picture. I'll show you the algebraic sort of description here in a minute. The slope here is 0. The tangent line is horizontal. But that point right there is not a maximum or minimum value. It actually doesn't fit the criterion. Okay? So this description right here where it says they are potentially places of local extrema really means that. Sometimes they are and sometimes they aren't. And if you were thinking about this in terms of derivatives, if I took the derivative of this and I took the 3x, or I got the 3x squared, and you take a look, sure enough, I mean, like, right, this equals 0. Right, this equals 0 when x is 0. It's definitely equal to 0, but you can tell very clearly from the graph that it is not an extreme value, right? It's this leveling off kind of place, but it's actually not an extreme value. So let's actually see how this plays out in a particular problem. The directions say to find all critical numbers by hand, and then use your knowledge of the type of graph that you have to determine whether the critical number represents a local max or a local min. Okay, so finding critical numbers by hand means doing exactly what I attempted to do over here. Taking derivatives and setting them equal to 0. So we're going to take the derivative of this one. And you know what the beautiful thing is once we get into chapter 3? The derivatives get easier to do. We're done with all the complicated, messy, ugly ones. You guys have that kind of stuff for the most part down now. And what you're going to see us doing with application is using functions that are easier and cleaner to work with. So that's a nice thing about chapter 3. All right, what's the derivative of this function? 3x squared, and then what? Minus 6x. Fantastic. And then what we're going to do is we're going to set this one equal to 0, because that's exactly what critical numbers are. Critical numbers are locations where our derivative is equal to 0, by definition. So what we want to do is we want to solve the equation 3x squared minus 6x equals 0. What do you guys remember about solving an equation like that? You got to factor. That's really important. Because I have something that's not linear, it's x squared in there, I can't just move something over and divide by stuff. That doesn't work. We actually need to factor. So, Akil, you can factor out the 3x. Is that what you told me to factor out? Sounds good. What's that going to leave me with? X minus 2. Awesome. All right, and then I'm going to set each part of this equal to 0. What do I get from my x values? 0 and 2. Everybody good with that? All right. Now let's take what we know about a cubic graph. This is what it said. It said, use your knowledge of the type of graph. All right, so this is a cubic graph, right? So a cubic graph, one of them I drew over here was the x cubed graph. Cubic graph has this basic look, right? But it might have things that look more like this too, right? Where it's got sort of peaks and valleys in between. That's another possibility, okay? But what we do know about the cubic graph is that if the coefficient here is positive, then it opens up on the right and down on the left. That's a feature of cubic graphs. One branch goes up and the other branch goes down. And if it's a positive x cubed value, it's up on the right and down on the left. If it were a negative, it would flip it, right? It would be down on the right and up on the left. So this right here is our knowledge of cubics. And if you are unsure, you've got a calculator. Remind yourself your knowledge of cubics, okay? All right, but you've got two places where it levels out, agreed? So the graph actually has to look like this one that's circled here with the blue in it, right? Because I've got two places where it actually levels out. I can't have this graph right here because that's only got one place where it levels out. So on this one, what I know is I know that this has to increase and then it has to decrease like this and then go back up. I've got two locations. The first location is at x equal what? That's 0 because it comes first on the number line. And the second location is at x equals 2. So I know that I've got a maximum here and a minimum here. Right? Now, this actually is enough for this problem because it says critical numbers and whether the critical number represents a max, min, or neither. Okay? What if instead it had not said numbers and it said critical points? What would it mean if it said points instead of numbers? I would need to find the y value. Do you know how to do that? Of course you do. You just plug it in the original equation. So be very careful, attentive to the language that they're actually giving you as to what they expect you to have for an answer. Here, you're done. You know that you have a local max at x equal 2, and you have a local min, I said it wrong, I'm sorry, x equals 0 was the first one. X equals 0, and a local min at x equal to 2. And that's sufficient. You're done. Any questions on that? I think that's our next one. It's got something else. Maybe I'm wrong though. Let me see. Yeah, the next one's not cubic. So let's take a look at what happens on that function, okay? All right. The next one is a critical number by hand problem. Same thing. And in this case, they don't ask us to do it based on what we know about the graph. They actually ask us to use some technology to make the decision. So the ones that they ask you to use your knowledge of the graph are going to be the ones that have that kind of a polynomial feel to it. So like they might have, instead of like an x cubed, it could be x to the fourth, right? What do you know about graphs that are even powers x to the fourth? What do you know about their branches on the end? They're either both up or both down. That's the kind of information. And then based on how many peaks and valleys you have, you'll know, do I have a peak and valley, a peak, or do I have a valley, peak, and valley, or is there just leveling off because I only have one critical point? So that's what you'll be doing on that. All right, so this one, though, doesn't have those directions. It actually says, if available, use a graphing technology to determine whether the critical number represents a local max, a local min, or neither. All right, so we're going to use a calculator on this one to actually answer the question, max, min, or neither. But this is a little bit of a more interesting one to do because what? It is a quotient, which means, Jen, we're going to need the quotient rule. Isn't that, yeah, so it's a little bit more interesting than the last one in terms of finding the derivative. Critical points, though. Whenever it says critical points or critical numbers, it means find the derivative, set it equal to 0. It's just one of those key phrases that you just need to know. When I see critical, it means find the derivative, set it equal to 0. So that's what we're going to do. All right, so what will the derivative be? And I would like to keep this as a quotient rule. It'll be easier to work with than turning it into a product rule. Some of you guys really love the product rule, which is awesome. But it'll be easier for us to work with if I just leave it as a quotient. So what are we going to get? Okay, so we're going to do the derivative of the top. Okay. Excellent. Okay. I'm going to put the times 1 just for the sake of seeing it. But yeah, and then divided by, what was that?
X plus 2 over x squared.
Awesome. Okay, is everybody good with that? There are a few of you who still want to switch the order on top. Make sure that when you're looking at the numerator of this, the numerator for the derivative, that it's the denominator that appears in the first term. Okay? Derivative of the numerator and the denominator that appears in the first term. All right, we definitely need to simplify this in order to be able to set this equal to 0 and solve it, right? So the denominator is simple. I don't want to mess with it. I want to leave it alone. We just want to simplify the numerator. So what do we get when we simplify the numerator? Okay, and I'm going to take one more step before I do that just so that I can show it. 2x squared plus 4x, and then minus x squared and plus 2. A few of you missed some signs in that particular instance when you were working on your test. So do be careful, really careful about those signs, because that will really wreak havoc on your solutions at this point if the signs switch. All right, and then on top, I had x squared plus 4x plus 2. Did I get all that in there right? I think so. Okay, now generally speaking, we talked about this when we did implicit differentiation. Our derivative equaling 0 or not existing create places where I have critical numbers. That's actually how it was defined back here. It said that critical numbers, or it said that relative extrema, rather, let me say it that way. Relative extrema are places where we have a max or min. The derivative is either 0 or doesn't exist. Now, this derivative does in fact not exist somewhere at -2. But I know I don't have any critical values there because what's happening at -2? It's an asymptote, right? A vertical asymptote. If I've got a denominator equal to 0 and there's no way to simplify it with the numerator, and there's not in this one, then I definitely would have an asymptote there. So I don't need to mess with the denominator. I really just need my numerator to equal 0. So my critical points are going to be where, so if I want to set the whole thing equal to 0, it's equivalent to asking where is the numerator equal to 0. Because if the top equals 0, I can divide it by anything except 0, and I'll have a 0 for my function. So I really just want to know where the top is equal to 0, and this is a little bit trickier And you had one of them on your homework. I think Mackenzie might have been the one asking me questions about it in my office, but now I can't remember for sure. Where you had to do a quadratic formula. Was it you and I that were talking about that one? We got a quadratic formula on this one too. This doesn't factor, right? Yeah, unfortunately doesn't factor. So we're going to have to use a quadratic formula. Let's see if I have another slide. I do. Awesome. So I had x squared plus 4x plus 2 equals 0. And I'm not going to embarrass myself and sing today, but do some of you guys know the quadratic formula in song? Yeah? Okay, good. Okay, we'll let you tell me. Okay, can you tell it to me with the b's and a's in there first, just to remind everyone? Okay.
Plus minus b squared of b squared minus 4ac divided by 2a.
You guys remember that? No? Some of you are going, nope, that's been a while back. So, yeah, this actually has a wonderful song that goes with it that I won't sing on a recording, but I'll sing it too when we stop the recording. All right, so we're going to do this, though, with A, B, and C plugged in. In particular, the A is the first part right here. It's an understood 1. B is going to be 4. And then C is going to be the 2. Okay? It's just in order. So I have negative 4 plus or minus what? 16 minus 4 times 1 times 2. That's going to be my 8, yep. And then all over 2 times 1. All right, what is the whole square root underneath simplified to? What is underneath the square root? It's an 8, right? And underneath is a 2 right now. And we want to be careful. We want to simplify that square root before we attempt to do any division. Don't attempt to divide the 4 and the 2 until you've simplified the square root. What will that be? 2 square root of 2. Fabulous. And then the 2 will actually simplify because there is a factor of 2 in all 3 of these terms, right? So we'll divide each of them out by 2, which gives me negative 2 plus or minus technically 1 and then square root of 2. This is 2 solutions. It's negative 2 plus square root of 2 and negative 2 minus square root of 2. Right? And they have decimal approximations, and that's cool. Just for the sake of argument, though, which one is on the left side of my graph and which one's on the right side of my graph? All right, so this one is the leftmost value, yeah? And this one's on the right. And what tells us that that's the case? Did we lose something? Oh, awesome. Okay. What tells us that the value, that the negative 2 minus the square root of 2 is on the left? Yeah. It's the fact that we're subtracting something right here instead of adding, right? Okay, good. All right, so grab your calculator. I want you to graph this. I'm not going to draw the graph, but I want you to graph this. I want you to tell me, based on the graph, what you see. Maybe I'll let you guys, one of you guys draw it for me. That's a good idea. Let's do that. I know that I have a horizontal asymptote, or vertical asymptote, excuse me, at 2, right? So you should have something like this going on at 2. You're graphing the original equation. Thank you for asking. Yes. Our goal is to graph the original equation because it says use graphing technology to determine if they represent a local max or min, and the graph will show us that exact fact. So we're graphing that. Oh, did I draw it wrong? Oh, I did. I'm sorry. Thank you. Well, you know what? Watch. Look at this. Look at that. Wasn't that fancy? Yeah. So now it's at negative 2. Okay. You have a graph. Yes? Okay.
I have to draw this.
It doesn't have to be perfect. It's just a sketch.
Okay.
That'll work. And the other half? Okay, is this what you guys got? Wonderful. And you got to play with an iPad. Woo! All right. So this one right here is the left point. And is it a max or a min? It's a max. And this point over here, roughly, is a min. And it is interesting, is it not, that the maximum is smaller than the minimum. So you can't just figure out, well, which one has the bigger value. It doesn't work that way. It's relative to where it is. It's located in a nearby area. Nearby, what's happening? Is it a maximum? Is it a minimum? So when we're answering this question then, we can say that we have a maximum at x equals -2 minus the square root of 2. And we have a minimum at x equals -2 plus the square root of 2. Any questions on that? Now, I'm going to guess probably, Akil, this would be a really good example of one where our prior knowledge of these graphs would not have been especially helpful here, right? I don't think mine would have been. And so I'm guessing probably the same is true for you guys. And that's why their directions actually indicated they wanted us to use graphing technology to help us with that piece of information, okay? All right, this is a good stopping spot.